Hi everyone, in this video I'm continuing to work through question 13 part D of the 2020 Extension 1 trial exam from James Ruse. So it's a two-part question and I've already worked through part 1 in a prior video, so have a look at that if you haven't already. In this video I'm going to focus on part 2, which tells us that Gabriel also swims at 60 meters per minute, but he is to start at position C on the diagram. And we're told that C is 60 meters upstream from position A. Now we're asked in which direction should Gabriel aim to swim in order to swim directly to position B under the influence of the current. And again, we're told to draw a vector diagram to demonstrate the velocities and show all necessary working out. And here we can round our answer to 1 decimal place, which kind of gives a little hint that perhaps the angles that we're going to get aren't going to be nice and clean like they were in part 1. So yeah, let's take a look. So here I've recreated our diagram here. So again, we've got our parallel riverbanks, our point A and B being 240 meters apart. North is pointing up as it was before. And the key difference here is now we're starting at point C rather than starting at point A. So we're told, as it was before, that the river is flowing from west to east at 30 meters per minute. And now we've got Gabriel, who I'll just call G, being also able to swim at 60 meters per minute. So the question here is, what direction should G swim if he's going to start at point C and end up at point B? So basically follow this vector, but noting that we've got the river flowing, we again can't just swim in that direction. We'll end up overshooting our mark. So just like before, we kind of need to start by thinking just a little bit logically. Obviously we can't swim in the northeast direction. That's kind of gonna get us to overshoot. I mean, possibly we could swim directly north, and depending on how it all works out, the river could could get us to B as we need. I mean, maybe we could go slightly northeast, so not like directly in the direction of B, but it could be slightly northeast, it could be northwest again. It's actually not as obvious as it was when we were starting from point A. So what I might do is I might just draw, maybe I'll just come northwest and just pick a point here, X. But it's actually still yet to be determined where X will actually be relative to C, whether it will be west or east of C. We'll have to do our working out to work it out. But for now, just for the sake of drawing something, getting a diagram going, I'm going to draw point X, and what we're going to do is we're going to go from C to X, and then we're going to go from X to B. So just like we did before, we're going to effectively get where we need to get to in this alternative route. So just like before, we can say that the vector CB we can get to by going from C to X vector plus X to B vector. And effectively, we're looking for this whole angle here, this angle XCA. And if that angle ends up being more than 90 degrees, so more than kind of going true north, this 90 degrees, then we know we're effectively going north and a little bit west. If it ends up being less than 90 degrees, this whole angle, then we know we're going north and then a little bit east. And so effectively, the size of this whole angle is what's going to allow us to ultimately write our answer. And what I might do, just in terms of working, is I might call this portion of the whole angle, I'll just call this alpha, and then I'll call this portion beta, because I think it's helpful just to break it up, given you can hopefully see we've got two triangles that we're working with here. So if we break up these angles, work them out individually, and then consider them in total, and then effectively work out whether we're going northwest or northeast. So hopefully that makes sense in terms of a strategy. In terms of thinking about these two angles, clearly angle beta here can be determined using this triangle ABC because it's a right angled triangle and we've got two of the sides. We've got our opposite side and our adjacent side to the angle. So I think a good place to start would be to say from triangle ABC, we can say that the tan of beta is equal to the opposite, which is 240, over the adjacent, which is 60. And hopefully you can see that's 4. But again, if you're like me and in exams you're prone to doubt yourself, you can just use the calculator to double check. Yep, 240 on 60 is 4. So therefore beta will be the inverse tan of 4, which I'm pretty sure you can't do in your head. So let's get our calculator for that. So inverse tan of 4 is, yeah, this kind of not very neat angle. So 75.9637563 and so on degrees. And we're told that we can use rounding to 1 decimal place. So in this case, actually it would end up as just 76.0 degrees is beta. Now, if you're worried about losing precision in multi-parts, you could just keep it at this unrounded and then only round at the final step. That's always kind of a sensible thing to do, just in case you lose a little bit of precision. But effectively, we're thinking of beta being, essentially 76 degrees thereabouts. So that's beta done. So now we need to think about alpha. I think we can use a similar approach, I'll just move my ruler, to what we did in part 1, where we kind of used our speeds to work out the magnitude of our other vectors. So I think we can do the same thing because once again, we've got Gabriel swimming at 60 meters per minute and the river is still flowing at 30 meters per minute. So we can say since G swims at 60 meters per minute, we could say that 60 would equal to the magnitude of the Cx vector divided by t. And again, that's assuming that Gabriel needs to swim for t minutes. Since G swims at 60 meters per minute, and maybe I'll say assume swims for t minutes. Assume that that's kind of how long he needs to swim. So therefore we can say that the magnitude of Cx vector is equal to 60t, just like before. So this will be 60t. And again, since the river flows at 30 meters per minute, we can say that 30 would equal the magnitude of xb vector on t, and so the magnitude of xb vector would be equal to 30t, just like before. Now, even though these may not be the same distances, we can still end up with 60t and 30t because it just may be that the t minutes is different in this particular scenario than it was in part 1, because we're just working with a generic t. We don't actually know the value of t, and just like in part 1, we won't actually need to work that out. But the process is the same, and now we need to think about how we can make use of that with triangle BCX, given it's not a right angled triangle, so we're not really going to be able to use our SOHCAHTOA rules. But I think what we can do, if we first of all note that we've got parallel lines here, so these angles here are alternate angles on parallel lines. So we know that this angle ACB we've called beta. That'll mean that angle CBX is also beta. And so noting that, we've got a situation where we've got a triangle where we know an angle and the length of the opposite side, and another angle and the length of the opposite side. And so that's enough to make use of our sine rule. And I might be worth just turning over at this juncture of the question. But what we can say, if I turn over, we'll say from triangle BCX. So from triangle BCX, we can say using the sine rule that the sine of alpha on 30t, the sine of alpha on 30t would be equal to the sine of beta on 60t. Sine of beta on 60t. And we'll see that these t's naturally cancel, which is why we don't really ever need to work out what t is. They cancel out. Now, remembering we're concerned with alpha now at this point, so if we wanted to isolate alpha, we could say sine of alpha is equal to, and we bring the 30 up, so we get 30 on 60 of sine beta. And then if we want to isolate the alpha, we'll get alpha is equal to the inverse sine of the 30 on 60 will reduce to a half. And then we've got our sine of beta, which we had worked out was this 76 degrees. Or if you're worried about losing precision, you could just insert the raw inverse tan of 4. So inverse tan of 4. And that way we don't lose any precision in this kind of two-step calculation. So that would mean alpha, if we want to plug this into our calculator, maybe I'll work from the inside out. That's probably the easiest way. So we'll get our inverse tan of 4, and then we'll take the sine of that answer, and then we'll multiply that by a half, and then we'll take the inverse sine of that answer. And we end up with 29.01714.062 and so on degrees. Or if we want to get that to one decimal place, that would actually just be 29.0 degrees to one decimal place. And if we have a look at our prior calculation where we put it to one decimal place, if we were to take the 75.9637 and we got the 29.017, I think you're going to end up with, you're not really going to lose precision when you add them both up and take it to one decimal place. So those numbers work out pretty nicely in the end. What can we conclude from all that? We can say, therefore, alpha plus beta, what is that? Well, it's, I'm going to say it's 29 degrees plus our 76 degrees, which equals 29 plus 76. I think that'll give us 105. Oops, 29 plus 76, I think. Yep, 105 degrees. And as I mentioned before, in terms of thinking, well, what's our direction? It depends on whether we end up with a total angle that's greater than or less than 90. Well, we've clearly got an angle greater than 90. So if we think about we're going north and then a little bit west, and the amount west we can work out as this angle taking off the 90, given going north represents the first 90. So we could say, therefore, G should swim north, and then it's actually, the amount west he goes will be 105 minus 90, which is 15 degrees. So north, 15 degrees west. And I reckon that's all you'd really need to do to get your marks for this question. So I think now that we've done that, it kind of makes sense that the amount west we're going is at least it's smaller than the amount west we went in part A. Because if you think about it, if we're starting from directly beneath point B, then we're going to have to point further west given the current to end up at B than if we're already starting to the left, like coming to the left. So I guess it's not clear whether you're going west or east before you do all the work, but now that we have done the work, it at least makes sense that the number we got was less than 30 degrees west. If it was more than 30 degrees west, maybe you'd want to closely double check your work, because that doesn't really make sense that you'd have to swim even further west given you've already kind of offset a little bit of the effect of the current here. So yeah, hopefully that all makes sense in terms of the working. I mean, it's really just replicating the concept from part one. I guess part one was almost like a warm-up to part two. It gave us a chance to get our head around what this question's all about and kind of thinking in terms of vectors and really bearings. And then part two, I guess the added complexity was that we ended up with two triangles, with one of them not being a right-angled triangle. So our sine rule came into play here. So you had to know both your SOHCAHTOA rules and your sine rule, but I think that's definitely fair game in an Extension 1 exam. So yeah, there you have it for that question. Hopefully it all made sense. And tick boom.